Chapter 9 is all about global circulation. Our driving question is, what are the principal features of the planetary scale atmospheric circulation, and how does the circulation affect weather and climate? In an idealized Earth that does not spin around, the distribution of energy would take place like you see here. The equator is warmer than the poles, and so the warmer air would rise up and make its way poleward, where it would then cool off and sink, and then the colder air would move to complete the circulation cell. So we have rising warm air and surface divergence here at the equator, and then at the poles we have sinking air and this type of circulation cell, which, as we'll see later in this chapter, is called a Hadley cell. But this is assuming a non-rotating Earth and a uniform solid surface, which we don't have, right? Our Earth spins on its axis, and we have a mixture of continents and seas that make things a little bit confusing. So when we take the rotation of the Earth into account and ignore for a moment the land masses, we see a much more complicated circulation pattern in this picture. So what we have here is that Hadley cell, which we just saw for the idealized Earth, where warm air rises from the equator, makes its way northward, sinks, and then continues the circulation pattern. We have that Hadley cell that stretches over the equator up to the 30-degree latitude north and south. So these are called Hadley cells, and you see the name right there. They're named after the scientist who discovered them. And that's one of the circulation cells. So what happens here when we have this surface convergence, so these, if you look at the direction of wind as it's circulating through these Hadley cells, it's converging here at the surface, uplifting and then spreading out, diverging aloft. So when we have winds coming together like that, we end up with a low pressure, right? Wind is piling up and the pressure turns into low pressure. And remember, low pressure is associated with uplifting air, unstable conditions, which we also see here. So right around the equator, we end up with these low pressure cells. As that air in those Hadley cells makes its circulation to 30 degrees north and south, it begins to cool off and sink. And what happens is the way the circulation cell completes itself is we have diverging air here, where the Ferrel cell meets the Hadley cell. And this diverging air allows for winds aloft to sink down, and we end up with the circulation pattern indicative of a high. So we have high pressure cells around the 30-degree line, north and south latitude. And then if we continue this, if we look at what happens with the Ferrel cell as the winds make their way poleward towards the surface, they are converging at about 60 degrees latitude, north and south, and we end up with another thing going on here. So we have, again, converging winds and a high pressure system that sits right around the polar areas in the north and the south pole. So we call this cell the polar cell. So it's a very complicated picture here, but the important thing to remember is this is all as a result of two things: radiational heating that heats the equator and keeps it much warmer than the poles, and a rotating Earth, which causes the sophistication in the circulation patterns. So here we have our low pressure around the equator, and you can see these are doldrums. There's not much wind here. The wind that's blowing around these high pressure cells, remember, it's going to be clockwise and out. So we get these very light winds that are blowing towards the equator. And then when we look up at the 30-degree line around this high pressure cell, as it starts to meet the low pressure cell, we have different kind of wind. We have these westerly winds, and this area called the horse latitudes, as we'll see in a moment. You can read about that in the book. It's called horse latitudes because the Spanish ships, when they got caught in these winds that were very light, they weren't going very fast. And so they had to start throwing things overboard. And unfortunately for horse lovers, guess what got thrown over? Up in the low pressure here, where we've got the polar cell meeting the Ferrel cell, we have what's called the polar front. So this is a very stormy area. And then finally, sitting right on top of the poles, we have the high pressure cells. So remember the different belts. So from 0 to 30 degrees, and then from 30 to 60 degrees, and then from 60 to 90 degrees. We have changes in the idealized circulation patterns. When we tie it all together with the actual Earth, which is made up of continents and oceans, as well as rotation, we have a very complicated picture. So we see the same concept here. This top picture here is for January, and the bottom one is for July. So northern hemisphere winter on the top and summer on the bottom. And we see right around the equator these low pressure cells, right, the equatorial low, and then the high pressure cells right around the between the around the 30-degree latitude line. And then the lows, the polar lows, and then we don't see what's happening right at the top where the high pressure is, the polar high. So you can see how these cells are not as nice and neatly organized as they were for the idealized Earth made up of just water, but they're pretty close. When you look at what's happening in the summer, it's warmer in the northern hemisphere, so everything kind of gets pushed further south. We see the equatorial low, not as pronounced here. These subtropical highs, as they're called, have sunk down a little bit lower and a little bit stronger than they are in the winter. The polar low has weakened compared to how it looked in the winter. So let's talk about these different features. So right around the equator, where we have the winds blowing the way that you see them here. So remember, around a high pressure cell we have counterclockwise flow in the northern hemisphere. So when we look at the surface winds, these arrows are representing the surface winds. So right around the equator, the winds are very weak, and we call this area the intertropical convergence zone. It's where the maximum heating has taken place, and we have that uplifting air and convergence happening. So converging winds, right, they kind of come together and cause that circulation pattern of uplift and the equatorial low. The trade winds are further north and south in the southern hemisphere, and this is where the winds are steady. This is where the boats, the ships from back in the day when we were traveling by ships, liked to be. So when they put their sails up, they could catch these steady trade winds and make their way across the ocean pretty easily. The high pressure cells that form around 30 degrees latitude, north and south, we call subtropical anticyclones. Remember, another name for high is anticyclone. So these are subtropical. The tropics exist around the equator and about 10 degrees, maybe to 20 degrees north and south. So we're outside of the tropics. We call that area the subtropical area. And you see the wind flow here. We have another name for these winds are westerlies when we get up above the 30-degree line. Excuse me. And then we have the polar front with the polar easterlies flowing around these low pressure cells, and this is the very stormy area that's, as we'll see in future chapters for this class, is representative for a lot of the mid-latitude cyclones, the weather that we get there. Same thing down in the southern hemisphere, same exact setup. Let's talk about the subtropical anticyclones. That's these guys here that sit at about 30 degrees north and south latitude. They're very extensive. They cover a large area over the ocean, and they have a major influence on the weather. So we have subsiding air that extends outward from their eastern sides. So the eastern side of these guys, we have winds that are subsiding. And what happens with that subsiding air is it warms as it sinks, as it subsides, due to compressional warming. And there's not much relative humidity because of that. So we have nice weather in these areas that are on the eastern side of these subtropical highs. And that's where most of the world's deserts are located. So if we could see the continents on this map, we'd see that this one sits just off the coast of the United States, and the desert, the Mojave Desert, that extends throughout Arizona and Mexico and larger areas, is a result of this subsiding air, this predominant subsiding air. So it's not conducive to storm development, and it keeps things dry, but it also keeps it sunny. The western sides of these high pressure cells are characterized not so much by subsidence, but more unstable air, and we end up with more cloudy and stormy weather. So those horse latitudes, remember, are up here around 30 degrees, where these pressure gradients are fairly weak and the winds are inconsistent and can be very weak. Now the winds that are blowing out of these high pressure cells towards the equator, these are the trade winds, these are the strong winds, but the ones that are kind of closer to 30 degrees are what we call the horse latitudes. The trade winds from the two hemispheres converge, and this is our intertropical convergence zone, or the ITCZ as it's called, and this is responsible for tropical weather. So converging winds and lots of moisture, there's a lot of instability, so uplift and cloud development and heavy rains. So areas that are located in this portion of the globe tend to experience two seasons, the wet season and the dry season, as that intertropical convergence zone kind of marches north and south as the seasons change. As we go poleward of the subtropical highs, we have these surface westerly winds that flow into the regions of low pressure. And the low pressure for us, we don't see it so much on this map. We have the Aleutian low and the Icelandic low in the northern hemisphere. Let me just zip back a few slides so you can see that. We'll look at the winter picture here. So here's the Icelandic low and the Aleutian low that are pertinent for our weather in the northern hemisphere. Okay, in the southern hemisphere, it's not broken up as much. The low pressure cell, the polar low, it's like a constant belt right along that latitude where the polar front meets, because there's not as much land mass, it's more water there. In these areas where the polar front is well defined, we get storm track. This is a common storm track. We watch this in the winter months especially to deliver strong winter storms to the United States. And then the polar highs that sit on top of the caps are very shallow anticyclones that just sit at the poles and actually keep the weather pretty sunny and dry right up there at the pole.